In this lecture, I am going to discuss mathematical expression and phase trajectories diagram for MSK modulation, minimum shift keying modulation. Now first let me look at the modulated waveform with the carrier. Okay, so when we go to the modulated waveform, let me start with the baseband expression, that is modulating signal. Okay, so we know that the modulating signal or the baseband signal is given by e power j times theta of t. Okay, so it's a exponential form, your baseband signal in the exponential form. In the exponential form. This form we arrived with a lot of assumptions. It's a magnitude, okay? It indicates the magnitude of the complex exponential or complex exponential form, and theta of t we know how it looks. Now finally, your modulated waveform is given as follows. So how do you get the modulated waveform? You take the baseband signal C of t, okay, complex baseband waveform. The C of t is complex baseband waveform, multiply by e power j omega naught t, the carrier frequency, frequency of the carrier. This omega naught is the angular frequency of the carrier. This also called passband waveform. Okay, now take the real part of this. So this is equal to C of t is e power j theta of t times e power j omega naught t, and take the real part of that. This is equal to real part of e power j times omega naught t plus theta of t, and take this. So that will be equal to cos of omega naught t plus theta of t plus j times sine of omega naught t plus theta of t, and take the real part of this. So anyway, this part will go to 0. So this is equal to cos of omega naught t plus theta of t. This is your modulated waveform or passband waveform. Okay, this is your passband waveform. Passband waveform where the theta of t is given as follows. Theta of t equal to where theta of t is given below your initial phase theta L plus or minus 2 pi times t minus LTB over 4TB. Now let me rewrite this. So this is equal to theta L plus or minus 2 pi times t by 4TB, then minus r plus 2 pi times L by 4. TB and TB will get cancelled. So this is your theta of t, right? Substitute this in this expression. Therefore, your modulated waveform S of t equal to cos of omega naught t. Omega naught t, let me write down as 2 pi f naught t plus theta L plus or minus 2 pi t over 4 TB minus r plus 2 pi L over 4. Right. Now again rewrite this equation as follows: 2 pi times f naught plus 1 plus or minus 1 by 4 TB times t. Okay, then minus r plus you take this 2 pi also L by 4, then look at the braces like this plus theta L. I can write like this. Okay, now look at here. I already appreciated the fact that this f naught plus or minus 1 over 4 TB Okay, so what is this? I can write as a plus or minus 1 by 4 TB as f naught plus 1 by 4 TB, then f naught minus 1 by 4 TB. Okay, so therefore this f naught plus 1 over 4 TB can be thought of as, or can be taken as, one of two possible frequencies. Therefore let me call this is frequency f1, and this is can be thought of as another frequency. Let me call this is frequency f2. Therefore in general this whole thing let me call by fi. When I equal to 1 I'll get this one, when I is equal to 2 I'll get this one. So there are two frequencies. Okay, so this fi is the frequency in that particular interval. So fi is the frequency in that particular interval. Okay, in that particular interval. Okay, now look at this expression, this one. Okay, and this is my s of t, and look at this expression. In this L by 4 basically takes care of the fact that every bit interval you either increase the total phase by pi by 2 or decrease it pi by 2. Basically this L by 4 indicates a phase increase of either increase, let me change the color, either increase pi by 4, sorry, pi by 2, or decrease pi by 2. How do you say it is pi by 2? Because if you multiply this by 2 pi at a particular bit interval, then you'll get 2 pi times L by 4, that is pi by 2. Pi by 2 into L. When L equal to 1, you either increase by pi by 2, 2 increase by 180. So it keep on increases or decrease because it is minus or plus. Right? So you have minus or plus L by 4 multiplied by 2 pi. That means what? Minus or plus pi by 2 times L. Okay, where L equal to 0, 1, 2, 3 and keep on it goes 0, 1, 2, 3 and so on. At particular bit interval, either you increase by pi by 2 or decrease by pi by 2. Okay, so this is the final phase change. The final phase change is going to be one more minute. Let me rewrite this equation. Your s of t is equal to cos of let me write 2 pi times fit minus or plus L by 4 plus theta L. Right? I can write like this, where fi equal to, already we know this fi is written here, written over there. Okay, so fi equal to, yeah, I'm sorry, the fi is here. Fi equal to f naught plus or minus 1 by 4 TB. This f naught is here. Okay, so this f naught is plus or minus 1, f naught plus or minus 1 over 4 TB. So therefore, you look at this expression now. If you look at here, then the final phase change is occurring gradually through this frequency change, this one, through this fi. Okay, and frequency change process. Basically, that's what the whole idea is. Therefore, now that corresponds to this one. This one corresponds to two frequencies. One is f1 and the another one is f0. The f1 is given here. F1 equal to this one and f2 is this one. Now the second part is, how do we describe this phase change of MSK? So there is a systematic way through that we can explain this. So the behavior can be expressed in terms of what is called the phase trajectory diagram. Phase trajectory diagram. So we know that the phase is given by your initial phase theta L plus or minus 2 pi times T minus L TB over 4 TB. This we already know this expression, right? Now basically the phase trajectory diagram I will draw here. No, I think my iPad is not including this figure. Anyway, let me do one thing. I'll stop this lecture at this point. In the next lecture, I'll continue this phase trajectory diagram because it is not, highlighted. It is not active now. Okay, let me summarize. So this is your baseband, complex signal. and that complex signal is given by c of t equal to e power j theta. Okay, and then that is your baseband model, baseband, complex baseband waveform. This one is, let me draw, this is complex baseband waveform. Baseband waveform. So how do you move from baseband waveform to passband waveform? You multiply this baseband waveform by e power j omega naught t, e power j omega naught t with your complex baseband waveform, and take the real part of that. So you combine these two guys together, you'll get this one, and then e power j theta equal to cos theta plus j into sin theta. Apply this formula. If you take real part, the imaginary part will go to 0, and you'll get this expression, right? Then this is your passband waveform, where theta is given by like this, and rearrange theta as follows, and finally substitute the theta value in this expression, rearrange the theta of t value in this expression, and then if you look at combine in this manner, then f0 plus or minus 1 by 4 tb. So there are two frequencies involved here. One frequency is f0 plus 1 over 4 tb, that frequency we called f1, and the second one is f0 minus 1 over 4 tb. What we can say is, at one particular bit interval we have the frequency of f1, and next bit interval we have the frequency f2, maybe or may not be. So therefore we have two frequencies, and there is phase change of the another important point is there is a phase change of pi by 2, and this pi by 2 is not occurring at the not occurring at the bit intervals. This is your interval, bit interval. The phase change is not occurring at the bit interval, rather than it is occurring gradually over the bit interval. Therefore the phase changes gradually over the bit interval. So if you have like this, then what is the advantage? There won't be any phase discontinuity. If there is no phase discontinuity, that means your waveform will not go to 0, okay, will not cross 0. That means it is a constant envelope signal that we already discussed in the previous lectures. Okay, so my laptop is not my iPad is not highlighted to include these pictures. Anyway, let me continue this phase trajectory diagram of your MSK in the next lecture. Thank you very much.